Chapter 4 Optimization. This chapter introduces design optimization. The goal of optimization is improvement. The Johnson's method of optimization is introduced in this chapter through illustrative problems. This helps students to solve many practical problems. Learning objectives. Number 1. Learners will be able to solve the design problem using an optimizing parameter. Number 2. Learners will be able to understand the concept of material selection factor (MSF). Number 3. Learners will be able to write a computer program to select the compatible material for the design of part from the material data. Para 4.1 Introduction. In the design of a mechanical part in the industry, it is necessary to consider three important points. Number 1, optimizing parameter. Number 2, material selection. Number 3, constraint on design parameters. Para 4.1.1 Optimizing parameter. The design of any mechanical part can be done by specifying the optimizing parameter. The optimizing parameter refers to the objective of the functionality of the part. There are a number of parameters that can be considered for optimization in the design process. For example, cost, deflection, energy absorption, etc. The minimization or maximization of this parameter is the goal. In design optimization, the design methodology of the mechanical part considering the optimizing parameter is studied. To get a unique solution, only one parameter is considered for optimization. Para 4.1.2 Material selection. The selection of the material is possible by the design methodology in design optimization from the pool of material data. Out of the total compatible material, the one which satisfies the optimizing parameter can be selected. It means unique material will be chosen out of the total compatible materials. Para 4.1.3 Constraint on design parameter. It is possible that constraint on design parameter, that is output of conventional design problem, may be imposed because of the physical arrangements of the part in the assembly. The solution to the problem where constraints on the design parameters are mentioned can be obtained using design optimization. Para 4.2 Illustrative problem 1. The simply supported bar is subjected to force F at the center. The length between the support is L unit. The factor of safety for the material is Fs. The diameter of the shaft should lie between d min and d max. Design the bar for minimum deflection. Solution. Write first optimizing parameter. In this problem, the optimizing parameter is minimum deflection. There are two significant steps in the solution of the problem. Number 1, initial formulation. Number 2, final formulation. Para 4.2.1 Initial formulation. There are three sub-steps in the initial formulation. Number 1, to write the design equation. Number 2, to identify the variables. Number 3, to decide the type of problem. To write design equation. There are three types of design equations which are used in design optimization problem. Namely, number 1, primary design equation. Number 2, limiting equation. Number 3, subsidiary design equation. Primary design equation. This refers to any equation which relates to optimizing parameter. There can be only one primary design equation as there is one parameter to be optimized. In this problem, the primary design equation can be written as delta equals to FL cube by 48 EI, where delta is deflection, L is length, and I is moment of inertia, F is force, and E is the modulus of elasticity. Limiting equations. This refers to equation which relates to the parameter on which there is a constraint. In any design problem, there is always a constraint on the stress developed in part. Hence, it can be written as there will be at least one limiting equation in the problem. In this problem, the limiting equations can be written as SB is less than or equal to SY by Fs, D mean is less than or equal to D less than or equal to D max, where SB is allowable bending stress, SY is yield stress in tension, and D is the diameter. Subsidiary design equation. This refers to any design equation which the design engineer feels fit to be included in the problem. It is possible that the number of subsidiary design equation may vary from design engineer to design engineer, but it is important to note that equations related to stresses developed in part must be included in the subsidiary design equation. In this problem, subsidiary design equation considering the bending stress on the bar can be written as SB equals to M upon Z. m equals to fl by 4, z equals to pi d cube by 32, and I equals to pi d raised to 4 upon 64, where m is the moment, z is the section modulus. Number 2, to identify the variables. To identify the variables, it is necessary to know which parameters are not variable. The parameter to be optimized is not a variable. The material constants like Young's modulus of elasticity E, shear modulus G, Poisson ratio mu, and yield stress Sy, etc. are also not variable. In this problem, parameters delta, Sy, and E are not variables, while the parameters F, L, Fs, I, Z, M, D, Sb are variables. The variables are classified into three categories, namely number 1 functional, number 2 limiting, number 3 free. Functional variables. The variables which represent the functionality of the part are called functional variable. The parameters of which value is given in the problem are functional variable. Thus, in this type of problem, F, L, Fs are functional variables. Limiting variables. The variables on which there is a constraint are called limiting or constraint variable. In this problem, D and Sb are constraint variables. Free variables. The variables other than functional and limiting variables are called free variables. In this problem, M, Z and I are free variables. Number 3. To decide the type of problem. There are three types of problem. Number 1, normal specification problem. Number 2, redundant specification problems. And number 3, incompatible or inconsistent specification problem. The type of problem is decided based on the number of free variables and the number of subsidiary design equation. If the number of free variables is greater than or equal to number of subsidiary design equation, then problem is called as the normal specification problem. If the number of free variable is less than the number of subsidiary design equation, then the problem is called redundant specification problem. An incompatible specification problem is a special case of redundant specification problem. Para 4.2.2 Final formulation. In the final formulation, a solution to the design problem is obtained. The final formulation is different for every type of the problem. The selection of the material out of the compatible material is made and constraint on the design parameter is also satisfied. To select the material, the following procedure is followed. We know Sb equals to m upon z. Substituting Sb equal to Sy upon Fs, m equal to Fl by 4, z equals to pi d cube by 32, we have Sy upon Fs equals to 32 Fl upon 4 pi d cube. This will result to d equals to cube root of 32 Fl Fs upon 4 pi Sy. Equation for the d is used to test the compatibility of the material. It is possible to have three different values for diameter d. The diameter is less than d mean. In such a case, the diameter is modified to d mean. The diameter d lies between d mean and d max. This is a desirable case and no modification in the value of the diameter is required. The diameter d is greater than d max. In such case, the material is rejected because it is not compatible for the design. Based on the above, the table can be drawn where serial number, material, Sy, equation for d, d modified, and remark are the columns, and the rows can be filled by using the values from the material. The next step is to select the material using an optimizing parameter. We know from the primary design equation delta equals to Fl cube by 48 EI. Substituting I equals to pi d raised to 4 upon 64 in equation, we have delta equals to 64 Fl cube upon 48 pi Ed raised to 4. Substituting d equals to 32 Fl Fs upon 4 pi Sy raised to 1/3 in the equation, we will have the term Sy by 4 by 3 upon E as the material selection factor. The material which has the least value of material selection factor is selected for the design because that material will have minimum value of deflection as seen from the equation. Thus, the table can be drawn where serial number, material, Sy, E, Sy raised to 4 by 3 upon E and remark are the columns, and the rows can be filled by using the values from the material. The material will be selected from the above table and the diameter of the bar corresponding to that material is the solution. Para 4.3 Illustrative Problem 2. Design the simply supported bar for minimum deflection subjected to following conditions. The factor of safety Fs, the force F should act at the center of the beam, the diameter of the shaft should lie between d min and d max, the length of the shaft should lie between L min and L max. Solution. This problem is the same as that of the earlier problem, excepting there is a constraint on length of the shaft. Optimizing parameter, minimum deflection. Initial formulation. Number 1. To write the design equation. Number 1. Primary design equation. Delta equals to FL cube by 48 EI, where delta is deflection, L is length, I is MI, and F is force. Limiting equation. SB is less than or equal to SY upon FS. D mean is less than D max. L mean is less than L max. Number 3. Subsidiary design equation. SB equals to M upon Z, M equals to FL upon 4, Z equals to pi d cube upon 32, I is equals to pi d raised to 4 upon 64. Number 2. To identify the variable. Functional. F, Fs. Limiting variable. SB, D, L. Free variable. M, Z, I. Number 3. To decide the type of the problem. Number of free variables NF is equals to 3. Number of subsidiary design equations are 4. As number of free variables is less than number of subsidiary design equation, the problem is redundant specification problem. Final formulation. To test the compatibility of the material, we know SB equals to M upon Z. Substituting SB equals to SY upon Fs, M is equals to FL upon 4 and Z is equals to pi d cube by 32, we have D equals to 32 FL Fs upon 4 pi Sy whole raised to 1 by 3. It is not possible to decide the compatibility of the material using the equation for D because the value of L is not given. There can be infinite number of values between L mean and L max. Such problems never lead to unique solution, hence they are called as incompatible or inconsistent specification types of problem. In practice, the solution to such problem can be obtained by assuming the value of L. As L is directly proportional to delta as seen from the primary design equation, L is assumed to be equal to L mean and the problem is solved as explained in illustrative problem 1. Questions. Number 1. Explain the concept of optimizing parameter as used in design optimization. Number 2. What is the initial formulation? Why it is required in the solution of the design optimization problem? Number 3. What are the different types of variable used in the design optimization problem? Explain the significance of each. Number 4. Explain in detail the concept of material selection factor. Field study. Visit industries nearby and check whether design optimization is practiced in the industry. Number 2. Generate the database of industries in India where the design department is playing an important and critical role. Write an email to the person in charge of the design department inquiring about the use of design optimization as studied in this chapter. Prepare the report of the work done as above and present it in the Socrates seminar.